not can be regarded as dynamical systems. And so I'm going to give you a brief description of the problems that arise in this. So I come from the CFA Center for Analytical Mathematics in Bangalore, and my collaborators are Jean-Pierre Raymond from the University of Toulouse and the students in TFRM. Now we have quite a few, about 45 in that. Shishir Chaudhary, who is submitting his thesis, and Deva and Mythily and Devandra Mitra, who are starting their thesis. As you see, we have a very large Bengali population contributed from Belur Math and also Narendra, among other things. So the basic questions, I would start with a differential equation. It could be an ordinary differential equation or a partial differential equation. And the basic question is, we would like to control the trajectories of differential equations to reach a desired profile, to reach a desired state or point by using a control. And the control could act either in the domain in which the differential equation is defined, or it could be acting on the boundary partially or on all the boundary, or it could be acting through some parameters arising in the differential equation, or it could be through the initial conditions. All these are very important for applications, and we also want to know whether we can control it in an optimal manner, because very often when we want to land our rocket very softly in the moon, for example, that is a standard problem given in this control theory course. You want to spend minimum fuel because you can't carry too much fuel. So optimal manner is very important. And can we use the control to stabilize the system? This is also very important because very often we are near a trajectory which is an unstable trajectory. So the system tends to go away from the trajectory, but you would like to be near that trajectory for various reasons. In that case, I would like to use the control to push it towards the trajectory that is desired. Now, another important aspect is you have some observations available. It's very important in oceanographic and atmospheric applications, where you have plenty of data, satellite data and other data available. Can we use them to build your control? Because that will be more efficient, and it will be useful because you should be also be able to calculate the control and apply it immediately, improve your system. So these are some of the basic questions, but I will just briefly indicate some things starting from finite dimensional system, which is the ordinary differential equations, where these questions are pretty much well understood thanks to electrical engineers in their systems engineering. Now the mathematicians have been giving a sound rigorous basis for this, particularly for the partial differential equation, where it becomes much more complicated because of the infinite dimensional solution space which is involved. Okay, so let us start with a differential equation. I am looking at in Rn, and this is a simple equation, linear equation. So A is a matrix, n by n matrix, and B is going to be our control matrix. The control vector could be an n vector, ut, which is sitting in Rn. So we want to know how to find the control u such that we start from y0, which is a vector in Rn, and reach at any given y1 another vector in Rn. Now there are basic questions. How do you decide the system is controllable or not? If so, how are you going to get it? So these are some of the basic questions. So I start with very simple examples, which is easy to understand. So this is a very sort of cheating because I have chosen a differential equation which is completely decoupled, but it's easy to understand nevertheless. So this is a simple matrix A, and B is, the interesting thing is I am trying to control only one component, not both. So you may suspect already it will not be controllable. So if you write out the solution, y2, you see y2 has not felt the effect of the control u. because y1 and y2 are coupled. The equations are completely decoupled. So the system is not controllable because y2 is not feeling the effect of the control u. So let me go to the another example. Now I have changed my matrix A like this. B is still acting on only one component, and I ask the same question, can I control the system? So here what happens is they both are in coupled systems. So if you eliminate one from the other, I end up with a second order differential equation. And this can be, here u can be chosen exactly what you want and arrive from y0 to y1. Because x will be y0 and x prime will be y1. So I have written this as a second order equation where x and x prime will be the two vectors. Okay. So this poses the question that A and B should have some interaction in some way so that your system will be controllable. So that answer was given by Kalman, an electrical engineer in the 70s, 80s. It is now very well understood and used routinely. So A and B should interact in this way. So you form a big matrix where you put the B matrix, then this is the product of AB. So this means the big matrix formed by putting B, AB, A square B, etc. up to A power n minus 1B. And this should have, this huge matrix can have maximal rank only n. So that maximal rank is available. If it is there, then you can say immediately the linear system. This applies only for linear systems, of course. Then it is controllable. What it means is you can start from any y0 and reach any y1 if this condition is satisfied. And you can do one more thing. Once you know the system is controllable, you can use optimal control theory, which tells you how to write down the minimum control minimum norm and with the explicit expression. So let me go back to my examples and see, does it satisfy the Kalman rank condition? So here, this is the matrix. In the first example, I have put A and AB, the controllability matrix B, and this is AB. See, the dimension is 2, so I have to have only first column will be just the vector B, which was 1, 0. The second column will be the product of A and B. If you recall, A was identity. So A into B will be just 1, 0. Obviously, this doesn't have the full rank and Kalman condition fails. So let me go to the second example. There the situation is different. This is the vector B and this is A into B. So here you have the full rank and Kalman's condition is satisfied. So it is controllable, which we saw by calculating by hand. So now let me go to PDE systems. You have the solution space now is infinite dimensional. We are not in Rn but in some function space which is going to be infinite dimensional. I can't use the rank condition anymore, but I have to find a version of the rank condition applicable in the infinite dimensional space. How do we suitably adapt it? Another problem in PDE systems is you have different types of equation. You have hyperbolic and elliptic and parabolic. So you want to know, in this case, I have started with the transport equation, which is the simplest type of hyperbolic type equation, and I want to know what I can and how I can answer for the controllability question. Okay. So let me write down the equation. So y is a function of x and t. X is ranging in this interval 0L and time t is ranging in 0 to capital T, and yt, this is the partial derivative with respect to t, this is the partial derivative with respect to x. So this is the equation which describes the transport of mass, transport of anything. So this is a very basic model, very important. So you give, usually for this first order linear equation, you give the initial profile, which is u of t at x equal to 0 for all time. This is the condition. And this is the control I am going to put. You remember ut was the control we had used earlier. So I am using the same notation. So I have this interval 0 L. So x is sitting here, and this is the time axis, and here I am applying the control ut. So how I should apply the control ut, so that if I start from the initial profile, this is given y0x, this is the initial profile of the solution. So I want to reach any given profile y1. So now first of all we have to worry about the solution existence, whether there exists a solution, and for smooth initial and boundary conditions, a piecewise C1 solution can be written down, and you can also have weak solutions, so that is not a very difficult problem. And in this case it's easy to check if I have y of tx in the form, say f of x minus t, then fx yd will be f prime of this, and y partial derivative x will be again f prime with the sign change, and it will solve the equation. So the solutions are going to be in this form. You can say that is what I have written in the next slide. Yes. So the explicit solution can be written in terms of the initial condition y naught of x minus t. So this will be for t less than or equal to x. In this case, it is going to be, this is the line where x equal to t. And below this line, you will have the solution everywhere. This is the y naught is given here, y naught of x. So here it will be like what it was, y naught of x minus t. And above that, along this line, what happens is along this line it's going to be the constant, and that will be precisely this value of the initial condition. But u is felt only here because we are applying the control only here. So in this region, the control is not felt at all. So the control is, that means you have a problem when the system will be controllable only for a large time. So if I start controlling here, and you see in this is my capital T, then up to here only the control U is felt, and in this portion you see the solution is in terms of the initial condition y0. There is no role of the control U that we are applying. So it is clear that if small t is, the capital T is small, I am not going to see the effect of the control. That means if I go for large enough t, then you see the whole region would have crossed, this line would have crossed the whole region, and I am going to have the effect of U in the entire region. So that is what is a typical behavior for hyperbolic equations. That is, you cannot control for small time, but time must be sufficiently large. Or I can interpret it that here the disturbances will take sufficient time to cross the domain. Here the domain length is L, so your time has to be bigger than L. And let me go to the next one. The contrasting case is the parabolic equation, which is a typical prototype, is the heat equation. This arises in many heat propagation, chemical diffusion, in many of these things. And here the properties are entirely different. So this is a typical equation. This is the Laplacian, which is the sum of all the second order derivative. That is, if u is a function of x1, x2, x3, it will be d square x1 square, d square x2 square plus d square x3 square. So this is the usual Laplacian, and xt is, you usually give the boundary condition. So this is my omega. So my x may be x1, x2, let's say. So then Laplacian I denote by d square by d x1 square plus d square by d x2. So this is my Laplacian operator, and this is evolving with respect to time. So again I give the initial condition is here. here, you could change and put F to be the control in the interior. You could act on the F usually denotes the source term. So for example, the heat is spreading in this domain. You could heat the domain at some point, or you could absorb, cool the domain in some point. That could be acting as the control that you are imposing. So those are known as interior controls. Earlier I showed that was in this example, this was the boundary control. So it could be either of this type. So now we want to know the interior control may also be localized. Now the difference is the heat equation has a regularizing effect, which means if you give the initial profile which is even having discontinuities, immediately the heat equation smoothens it out. Your solution is going to be very regular as soon as time t is positive, which means I cannot ask the same question what we asked earlier. Can I reach any state? For example, if the state is not regular, obviously your system will not reach, because your system can reach only regular states. So the question has to be changed in such cases. In the previous example, which was typically hyperbolic, it doesn't have the regularizing effect. In fact, whatever initial discontinuity that you put, it will propagate as a shock wave. It will continue to exist for all time. So that means the regularizing effect was not there before, but now it is there. So I have to change the question. The reachable set is not going to be the whole space. So exact controllability, that is, I cannot ask any state can I reach. I have to modify this question. Typical question that is asked is null controllability. What is null controllability? Can you reach the state 0? Because we often want to know whether the system is extinguished or it will blow up. So those are typical questions, because the 0 state is always regular. Your system might reach at some point or not. So that is a typical question. In that case, it is known that the null controllability holds for any time t positive and any open set on which the interior control acts. You see the difference in the earlier case, the time t was has to be positive. It has to be bigger than the domain length. In higher dimension, it has to be bigger than some constant depending on the dimensions of the domain, depending on the diameter of the domain. So here, the time can be anything. So this is the difference between the hyperbolic and parabolic. So let me go to the compressible Navier-Stokes. This is a typical model for compressible fluids, air for example. This is different from the incompressible Navier-Stokes in the sense that is the density equation is not there. It is slightly different and much less. So here the pressure is taken to be like this. So rho is the density, u is the velocity. I have chosen it in x could be in a domain omega in higher dimension, but I have written it in one variable for simplicity. The pressure P is given, usually taken to be a power law depending on the density. So then we can ask the same question whether I can control the control of fluids is very important, because over the turbulence over the aircraft wings has to be minimized. We have to control. We have to know where to how to control this, minimize the turbulence. Because when the aircraft takes over, the other aircraft cannot come immediately because it leaves a wake. There is a turbulent region where the other aircraft might get disturbed. So we would like to know how we can control these things and how optimally we can do. So these are important questions. Numerically, the engineers have been doing. Only recently this mathematical study has been initiated. The difficulty here are, first of all, this is a coupled system. Rho and u are coupled now. And another difficulty is the first equation is of transport type. See, it is like ut plus ux. Okay, that is a transport type. The second equation has a uxx is a typical Laplacian type behavior. So the second equation is parabolic type. So one has a smoothening effect, the other has a non-smoothening effect in regularity. So we would like to, so the difficulty is apply for parabolic equations are very different from the techniques that you will use, tools that you will use for hyperbolic equation. Now what are we going to do when the system presents itself in a coupled manner? So that poses some difficulties. And another question is non-linearity. All the previous systems were linear. So what we have understood well is a linear system. How are we going to extend it to a non-linear system? So let me mention some existence and uniqueness results and the questions. The Russian school have they have studied very well. Kashikov and some of his many of his students, they have been working on it. Smaller in US, smaller and half have been studying. The main question they study is the rho should not become zero. That is the creation of vacuum. If rho becomes zero, density becomes zero, that interprets a vacuum is created. That has to be avoided, and so that is the question mainly studied. So we wanted to see whether we can control the fluid. It's difficult to go to the non-linear system, so can you at least look at the linearized system and study the control aspects, and then can we pass on to the non-linear system. So this is what I want to describe quickly in the remaining 10-15 minutes. So my domain is in one variable, a bounded interval. Let's take it as 0, pi, because I want to construct explicit solutions. So I'm going to take the steady state solutions as constants. Q0 is a positive constant for density, V0 is a positive constant for velocity. So these are clearly steady state solutions for the system. And V0 may even be 0, that will be simpler for me to analyze first. So I linearize the original non-linear system around this solution. That means in the earlier case, wherever I had a coupled non-linearity rho u square x, I will evaluate the derivative at the point the q0 okay. So that's how I end up with this linear system. And you can put an interior control, which is f into chi of O. This is the characteristic function acting on an interval O, a sub-interval of 0, pi. You can also have initial, you have to have initial and boundary conditions. So the boundary, the initial condition is rho naught and u naught for the density and for the velocity. And the boundary conditions could be your control for the velocity. So here we are trying to ask the question, you have a coupled system for two variables, the density and velocity. Can I control the entire system by controlling one of the variables, which is velocity? So that is why I am asking for controlling only in the second equation, which is for the velocity, or the boundary conditions, which is for the velocity. So the answer is yes, it is enough to control one variable, so that I will try to explain now. Additional boundary conditions may be needed when V0 is positive. So you can have internal control or boundary control. So now we have to put it into a mathematical function space framework, where you will look at it as an infinite dimensional differential equation, in exactly like we had an ordinary differential equation posed in RL. I will look at it as a differential equation posed in an infinite dimensional function space. For that we need to set up an operator, this is and use the semi-group theory, so that finally my solution will be the flow generated by this ST. ST of acting on initial condition will give me the flow of the, or which is the solution of the system. So I am going to look at the square integrable functions L2, L2, that means the density and velocity are sitting in this space. We will have a suitable inner product that should give me a Maxwell monotone operator, which means rho u comma rho u should be greater than or equal to 0. So I end up checking this. So you have to define the domain. These are, in fact, these are unbounded operators. So these are going to be not defined on the entire domain. So you have to suitably restrict it to a subdomain, which is my dA. And sorry, yeah. So this subdomain will be a dense subspace of my original space L2 cross L2. So here in this dense domain it will be defined because this d by dx is defined as well as d square by dx square is defined. Okay. So on this domain minus a is going to be an infinitesimal generator C0 semi-group St of Z. So once I have this, I will be able to write down the solution in terms of the semi-group and then study the properties. So let me go to the notation. So U, capital U will be the couple rho, the density and the velocity. So the system without control will be this. So you have the initial condition coming from the original space L2, L2 cross L2. And you see it is very similar to the ordinary differential equation that we initially saw, except that now this capital UT lives in the infinite dimensional function space. For every U naught in Z, there is a unique solution U which I can write as S of T, that operator ST acting on the semi-group ST acting on U naught. Okay, so we have the flow given by the theory of semi-group. But now what I want to do is, if I can write down the spectrum of the operator A, it is a lot easier because I can break down the space into invariant subspaces and do some Fourier analysis and add them component wise, and we may be able to say more answers to our original questions. So that is what I am trying to do, and luckily in this equation what happened was, if I take the rho to be cos nx and the velocity to be sin nx, remember the velocity is satisfied zero boundary condition, so I can allow only sine functions for the velocity component. So these, the space generated by this cos nx 0 and 0 sin nx will be invariant. That means a solution of this type will be C1 times this plus C2 times this. So that's how I got the invariant spaces, which were the Vn's. Okay. So restricted to Vn. Now the Vn is two-dimensional. So I can restrict my operator A to this two-dimensional space, and that will be a matrix. And for that matrix, I will be able to find the eigenvalues. Then I have to prove these are all the only points in the spectrum. And then I have the orthonormal basis. I have normalized this. I have normalized these functions so that these are orthonormal, and I write the whole of Z to be the orthogonal sum of these subspaces Vn. So that means I have finite dimensional subspaces which add up to the whole infinite dimensional subspace, infinite dimensional space. So the advantage is I can restrict my original differential equation to each of this finite dimensional subspace, in which I will see only ordinary differential equation for which the theory is well understood. So I will be able to say something. Now my question is, if I know the answers in each of these finite dimensional subspaces, can I sum them up and get it in the whole infinite dimensional space? So that is the way we approach this problem. Z0 is the orthogonal sum where I have killed the constants. These are without any constants. So that is why this the mean zero condition is used. You remember phi0 is the constants for the rho. So that will not live in this Z0 space. Okay. So what is how does the spectrum look like? So maybe I describe this in this picture. Now I have described the spectrum of A, but I should draw the spectrum of minus A because that was the infinitesimal generator of my differential equation. So the spectrum of minus A will be like this. It's all in the right. That was A was in the right half plane, so this will be in the left half plane, in the complex plane. So it has a finite number of complex eigenvalues, and then it has an accumulation point which I have denoted by omega naught, where the real sequence of eigenvalues are accumulating here, and there is another sequence which is going off to minus infinity, because I am describing the eigenvalues of minus A, which are the negative of what I have written in my slide. Okay. So what is the interesting thing is, is, if you look at the heat equation, you know already that if you look at in one dimension, x double prime minus x double prime is equal to lambda x. The eigenvalues you know will be this n square depending on the interval, n square, n going to infinity. So here it is a similar behavior, n square it will be also behaving like n square and it goes to infinity. So this is very similar to a parabolic type of operator, and this is the sectorial, in the sense I can put all the spectrum in a sector and it will have the behavior. So by looking at the spectrum we can guess the behavior is going to be like a parabolic equation, and it does happen. Then we have also written down, the only strange thing is this accumulation point, which doesn't happen in the case of heat equation. So let me go to the linear. So now we ask the question, can we bring the linearized system to rest in time t by controlling the velocity? So I have written the system. Now my control is ft, which is an internal control. I want to control only the velocity component. So I have taken 0, f. 0 for density, no control for density. The only velocity is controlled. So as I said, we can use the Fourier basis in Z0 and write the control ft in this form. So now what I want to do is project this system into my finite dimensional invariant spaces. So I describe the method now. When a basis is available, you can try building the control by using either a projection method or a moment method. We tried here the projection method. You project it on finite dimensional spaces, or the finite dimensional system is controllable. Then find a minimum norm control. I mentioned in the first few slides Kalman rank condition. You have to check B, AB, A square B, etc. Form that matrix and ask whether it has maximal rank. So that happens here. We have a two-dimensional system and it satisfies Kalman rank condition. So I will be able to write down the minimum norm control. So I have on each subspace a control. So what happens to the total sum? So can I sum up and get an L2 control? So that is the question we answer. So this is the projected system on each Bn, and the initial condition is also projected. Each Bn is two-dimensional. So I have a system in R2. So it's an ordinary differential equation for the coefficient of the components. So this is the expression I have just written for the optimal minimum norm control. So now you demand whether you can reach 0 or not. This is the null controllability step. So if f is in L2 cross L2, if and only if I can sum all the fn square, sum it from n equal to 0 to infinity, that must be finite. That will happen if and only if I write down the minimum norm control. I have written down this is my C times these components. So these components must be finite, and this and this, they depend on n. I have not written, but they depend on n, and I know the behavior of n because they will depend on the eigenvalues. Eigenvalues, I describe the behavior. One sequence goes to infinity and another sequence is bounded. So I will be able to determine, and that's how I mentioned this theorem, that it is controllable, but it's a very bad control in the sense you have to control in the entire domain, plus the first component has to be very regular. H1 means the rho is in L2, also the derivative is in L2. So it demands regular control. Otherwise it's not controllable. That is the conclusion. So you can ask the other question. Suppose I don't linearize at B not equal to 0, but I linearize at B not positive. Then what happens? Then can I do all this? There, interestingly, the system changes. So we looked at this with periodic boundary conditions. Now again, we took periodic boundary condition because I wanted again sine and cosine to be a solution, and then write down similar breakup. Now what happens is, the system, the spectrum changes. I haven't described that, but the spectrum will be not like this, but it will not have an accumulation point. but it will be along this, like this, that is, the points are all, the eigenvalues are all separated, but the real part is going to have accumulation point at minus omega naught like before, and one sequence going away to minus infinity. Now it is no more sectorial and it will not be an analytic semigroup, and this is a very typical behavior for a hyperbolic system. You see the eigenvalues are going to plus infinity, the imaginary parts are going to minus infinity and plus infinity, which is a typical behavior for hyperbolic system. So that is, then we know that controllability results can be expected only for large time sufficiently large, and that does happen. Here you can see what we got through the moment method. Null controllable with regular interior control only if t is larger than 2 pi by v naught. V naught was the play around which we linearized. Okay. So this is a typical behavior like a hyperbolic system in this when I linearize around. So the behavior is contrasting. When I linearize around this, there was no transport and the parabolic part dominated. When there is transport, V naught is positive, there is a transport component and it is behaving like hyperbolic. So the coupled system changes the behavior. So next question is, can I stabilize the system? Yes, if the spectrum is in the negative half space, you can expect stabilizability. So we ask at what rate of decay, and we try to answer, yes, it is stabilizable up to this omega naught. It is, although we cross some eigenvalues, it will be, you can stabilize up to, that is the solution goes to 0 like e power minus sigma t, where sigma is lying between these two. That is what we try to show in this. Here the difficulty is, if you cross, we wanted to know whether you can cross omega naught. Once you cross omega naught, as I said, this is an accumulation point, so you will be crossing infinitely many eigenvalues which will become positive, and then that all those modes could destabilize your system, and that was the difficulty. So we showed again by projecting to finite dimensional systems. We found the expression of the minimum norm control, and we showed that the minimum norm control goes to infinity as n tends to infinity, which means this is the best rate of stabilizing control. So let me go to the theorem says you cannot do beyond omega naught. Omega naught is the best one. Now further questions, I have another 2 minutes, let me finish. Okay. So you can, actually the system should include temperature also, so you can consider that. But the behavior is again like parabolic system. If you linearize around velocity equal to 0, then you can look at the nonlinear system around the stationary solution. See, because we wanted to stabilize the original nonlinear system, it can be done. You can do locally near a constant steady state using the feedback control for the linearized system. So this is what is. Then you can, if you want to study the higher dimensional system, so whenever we want to study the system, we usually look at the case where the Fourier basis is known. So there you can answer some things, and then you can also answer the optimal control problem. So let me summarize here. So one case it is parabolic, one case hyperbolic. Nonlinear system is stabilizable. Now there are many questions open. We don't know how to answer all these questions, which are ongoing work. So some of the references in this case are, this is the book by Mitter, is an electrical engineer from MIT, and Ben Susan, Prado, and Delfor. Delfor is also Mitter's student. This has the entire finite dimensional, infinite dimensional thing, and Zabzik is also, it's a very good book for starting control theory. These are some of the results that